Okay, yeah. So welcome back to the analysis seminar. Our first speaker this week is John Fraser, and he'll be speaking about a nonlinear projection theorem for Assouad dimension and the distance set problem. Okay, over to you.
Okay, thanks very much, Natalia. So I'm going to try to share my screen, as I've been learning to do in the last couple of weeks with my analysis lectures, but I've not done it on this platform. It's been on Teams, but it's roughly the same thing. So anyway, hopefully now you can see just a blank bit of paper. Please let me know if something needs put in focus or if I write off the page or something like this. I do still occasionally do this. Okay, so yeah, I want to talk about, so Natalia already gave the title, but let me just write it again. I'm going to talk to you about a nonlinear projection theorem. So most projection theorems which you've come across are linear objects because the projections that are being studied are linear maps. But I'm going to study nonlinear projections. So I'm going to shorten the title a little bit. So I'm going to tell you about a sort of very general story culminating in this abstract projection theorem for Assouad dimension. But what I'm really going to be interested in is applications, and the applications are going to be to the distance set problem. I'm just trying to get my thing in focus here, which I'm not managing to do very well. Sorry, bear with me. I take it it's just as fuzzy for you guys as it is for me. Okay.
That's good, man.
That's better. Okay, thanks. So yeah, I'm going to talk about a nonlinear projection theorem and then applications to the distance set problem, which probably many of you have seen before. So just a brief recap on the usual type of projection theorem that people in fractal geometry, geometric measure theory consider, and that is the orthogonal projections. So this is the sort of Marstrand, Mattila, Kaufman type thing that probably everybody has heard a lot of before. I heard about a lot before. So the basic idea is we take a set F in n-dimensional Euclidean space, and then we're interested in subspaces, subspaces of dimension m for some m smaller than n. So V is an m-dimensional subspace of Rn, and this is the Grassmannian manifold consisting of all such objects. So V is just one of those guys. And then what I'm interested in is studying geometric properties of the projection, which I'm going to denote by pi V of F onto the subspace V. So V here is the subspace, pi V denotes orthogonal projection of Rn onto the subspace V. And of course, the geometry of F should be related in some sense to the geometry of the projection of F. And the basic picture is you have some set F, this is drawn in the plane. And if I'm in the plane, then the subspaces are one-dimensional, so they're lines. So here is V, here is F, and here is the action of pi V. And then I have a set down here, which is pi V of F. Okay, so the seminal result in this area is from Marstrand. 1954, although it was the version I'm going to state is due to Mattila, I think 1975, but the original result was in the plane, and that was due to Marstrand. And it says that if F in Rn is, let's say, Borel, then the Hausdorff dimension of the projection of F onto the subspace V should be equal to the minimum of M and the Hausdorff dimension of F for almost all V in the Grassmannian manifold of m-dimensional subspaces of Rn. And here the sort of tricky thing, or the interesting thing to discuss, the statement is that the almost all is with respect to the natural Grassmannian measure on the space of m-dimensional subspaces. So this Grassmannian manifold comes with a natural measure. And when I say almost all, I'm talking about with respect to that measure. So the Hausdorff dimension of f is clearly an upper bound for the Hausdorff dimension of pi v of f, because the projection is a Lipschitz map. And also m is clearly an upper bound because the projection pi vf lives in an m-dimensional space. And so this is clearly an upper bound. In fact, it's an upper bound for all v. But the interesting part is that the lower bound holds for almost all v. So that's the classical Marstrand situation. So I'm interested in this talk mostly about Assouad dimension, and people have probably heard me talk about Assouad dimension many times before, so I'm not going to define it or really talk too much about what it is. But it's a different notion of fractal dimension, and you can ask the same sort of question. So if this Marstrand theorem explains the dimension theory of, or the Hausdorff dimension theory of orthogonal projections, then you can ask about the Assouad dimension of orthogonal projections. And this is something I've been interested in from time to time. And the result we've managed to prove is as follows. So this is probably from 2017. So the Assouad dimension, which I'm going to denote by dim A, of pi v f is at least the minimum of m and the Assouad dimension of f for almost all v in G and M. So it's a sort of similar result to the Hausdorff dimension result, but there are various notable differences. For one, I don't need any assumption about the measurability or set theoretic structure of f. F can be any set. Also, what I said before about the Hausdorff dimension of this being a trivial upper bound, it's not a trivial upper bound for Assouad dimension, and this is because Assouad dimension can increase under Lipschitz maps. So just because pi v is Lipschitz doesn't mean that the Assouad dimension of pi vf can't be bigger than the Assouad dimension of f. So this is an extra difficulty that comes in here. But then the most striking difference, and the most important difference for this talk, is that the equals sign is replaced by a greater than or equals to sign. And you can't improve this. So you can't generally make put an equality here. And in fact, the behavior of the Assouad dimension above this almost sure lower bound can be as wild as you like. So it can take on multiple values with for positively many subspaces. It can even you can even construct examples where there is no value that this takes on a set of positive measures. So all sorts of strange things can happen above this value, but at least we have this almost sure Marstrand-like lower bound for the Assouad dimension of pi vf. So this is something I've worked on with Tuomas Orponen, Antti Kanmäki, and others over the years. Others I'm forgetting, but I've certainly worked with Orponen and Kanmäki on this problem. Okay, so let me briefly deviate from the world of projections to talk about the problem that I want to eventually get round to by the end of this talk, and that's the distance set problem. And I'm probably going a bit slower than I hoped, so I'm going to just whistle through this. So the distance set problem is, again, you take some set in Rn, and to it you associate what's called the distance set, and I'm going to denote that by capital D of f. And this is simply the set of all distances formed by pairs of points in the set f. So just written in a compact form like this. And the distance set problem, which originates with a paper of Kenneth from the 80s, asks to relate the dimension theory of the distance set to the dimension of the original set. And so the most common way of formulating this problem is in terms of Hausdorff dimension, but of course there are many other natural ways of defining this problem. You could use a different notion of fractal dimension. You could talk about Lebesgue measure, that sort of thing. But here's one conjecture, which is open for all values of n at least 2. So of course there's different versions of this problem if you change n, but the problem's been getting a lot of attention in the last few years from people like Pablo and Thomas Orpinen and Alex Josevich and his collaborators, etc. But most of this attention has been in the planar case, so the case when n equals 2, but of course the conjecture I'm going to write down makes sense for any n. And that is, let's suppose f again is Borel, then if the Hausdorff dimension of f is at least half of the ambient dimension, so f here is a subset of Rn, if the Hausdorff dimension of f is at least n over 2, then this should guarantee that the Hausdorff dimension of the distance set of f is as big as it possibly can be, which is 1. So note that the distance set lies in R. So the biggest the Hausdorff dimension could possibly be is 1. So the idea of this conjecture is that if the set f has large enough dimension, then the distance set must be maximal dimension. So here's another version of this conjecture, which is going to be more relevant for me, and that is that the Hausdorff dimension of the distance set of f should be at least the minimum of 1 and, let me get this right, 2 over n, the Hausdorff dimension of f. So this is this second conjecture implies the first one, clearly, if I've written it correctly. But it tries to explain what happens when you have sets with Hausdorff dimension less than half of the ambient spatial dimension. What we expect is that there should be some lower bound like this. And this problem is open, but as I've said, there's been lots of wonderful progress, people like Pablo and various others in recent years. So the connection between this problem and the projections problem is going to come via nonlinear projections, as you can probably guess. But one way to see this connection immediately is just by considering, instead of the distance set, consider the pinned distance set. So this is the same setting as above, so f is a set in Rn, but this time I'm going to fix a point x also in Rn. X may or may not be a member of the set f. And then the pinned distance set, which I'm going to write as d subscript x of f, is just the distances formed between x and points in f. So it's a related set to the distance set, but now I'm pinning the point x, and then y can vary over f. Now, if you think about what this map is doing, so again, I'm going to draw something in the plane. So if I draw the point in the plane x here, then if f, so let's suppose, well, let me draw f. So f is maybe some sort of fractal set which is lying over here. Then what is the map which takes a point y in f and maps it to the distance? Well, I can think of this as some sort of circular projection. So if I identify the positive real axis, or if I put a sort of translated copy of the positive real axis translated by x, and place it here, then if I move the point y along a circle centered at x with radius, the distance between x and y, then it will hit the real axis translated by x at exactly the distance between x and y, right? And so I can then, move all of the points, here's another point in f, along these circles. So I take the whole of f, and if I project it along these lines, then what I'll get is a set here, and that's going to be precisely the pinned distance set of f with respect to x. So what's happening, this sort of looks a little bit like orthogonal projections, except instead of moving along straight lines and projecting onto a plane or a line, we're moving along curved lines. So this is the connection to nonlinear projections, essentially. So the pin distance map can be thought of as a nonlinear projection, specifically a circular projection. I'm just going to write circular projection and put it in a cloud for no particular reason, but that's just to emphasize that that's an important connection between distance sets and projections. Okay, so if we've had orthogonal projections and distance sets, which you can think of as circular projections, then I want to just mention one more type of nonlinear projection, which is also going to be relevant, and that's radial projections. So this time, so again, I always have a set F sitting in Rn, and this time I fix, well, similar to the setting before, it really exactly the same. I fix a point X in Rn, and then this time I'm going to, instead of projecting along circles, I'm going to project along radii. So I draw a circle, a unit, so it actually doesn't matter what kind of circle I draw, but let's suppose it's a unit circle in the plane, or a unit sphere if we're in Rn, centered at X. And then again, here is my fractal F. This time I'm going to project it along radial lines. So this point Y in F is going to project towards X, and then when it hits this circle, it's going to stop. So this point here is the radial projection of Y in the direction X. I'm going to denote that by pi X, Y. So far we've met orthogonal projections pi V. So this is our projections onto the subspace V. We've met the distance, the pin distance map, which is like a circular projection, and we've met radial projections, which I'm denoting by pi subscript X. So hopefully it's not too confusing to have so many different types of projection going on. I'm going to have at least one more. So radial projection, so if you have a dimension, a well-established and well-known theory of orthogonal projections in this context, then there's also a perhaps equally well-developed theory of radial projections, and you see a similar Marstrand type phenomenon occurring again. So for example, so if I say Marstrand theorem, I don't think Marstrand studied radial projections, maybe I'm wrong about that, but let me just, it's a Marstrand type theorem. Again, if F is in Rn Borel, then for almost all X in Rn, and this time the almost all is just with respect to n-dimensional Lebesgue measure, pi X of F, so this is, I'm varying the point where the circle is centered, and then I'm considering the radial projection of a fixed Borel set F. Then this, forgot to write dimension, the Hausdorff dimension of this set is almost surely what it should be. So for almost all X, the Hausdorff dimension of the radial projection of F is the minimum of n-1 and the Hausdorff dimension of F. So it doesn't look exactly the same as the Marstrand theorem, but it is, because you think the natural guess for the dimension of this set should be the Hausdorff dimension of F, unless of course this number is too big. And what does too big mean in this context? Well, you're projecting onto the surface of a sphere in Rn, so that has dimension n-1. So the upper bound, the trivial upper bound this time is n-1. And again, this time, if you vary the pin, or the point where we're projecting towards, the best guess for the dimension is achieved almost everywhere. So this is a sort of Marstrand type phenomenon, which also happens for these radial projections. Okay, so now I'm going to talk about nonlinear projections. So this section is going to be, or not really a section, this theorem I'm going to state is abstract. And this is simply because I want to be able to use it for many different families of nonlinear projection, especially the pin distance map and the radial projections, which I've spoken about, or equally well, the orthogonal projections if I wanted. So nonlinear projections, this is something I proved this year. So it's going to be abstract, but hopefully you'll see sort of roughly the type of families of projection that I'm able to handle. So this is the fourth and possibly final different family of projections I'm going to have, but this is the abstract family. And this is supposed to be a capital pi. So I don't know how clear that is, but this is a capital pi, which is different from the small pi's I've been using for radial projections and orthogonal projections. And it's indexed by t. So I'm considering a family of projections pi t, where t belongs to some parameter space omega. So omega is a metric space, but so omega could be the Grassmannian manifold, or it could be Rn, or it could be something else, depending on what family of projections I'm considering. So this is I'm eventually going to say things for generic t in omega. And so for that reason, I want a measure. So mu is going to be a Borel measure on omega. So that's the setup. But this is extremely general. Well, I haven't told you what pi t is yet, so it's not really it's not even an extremely general setup. It doesn't mean anything. So let me tell you some facts or things I'm going to assume about this collection. So for all t in omega, I want capital pi t to be a map from Rn to itself. Okay, so now at least it makes some sense. I'm looking at parameterized families of maps from Rn to Rn. Now it's just a very general family, which of course I can't say anything about if I don't make more assumptions. So here's another assumption. I want for all z in Rn and for mu almost all t in omega, I want capital pi t to be C1 and of constant rank M in a neighborhood of Z. So what does that mean? So pi t has the whole of Rn as a domain, but I want, no matter which point I choose in that domain, almost all t are going to have this nice form where pi t is differentiable, and moreover so if I differentiate this map, the derivative is going to be a Jacobian, and I want that Jacobian to be a matrix of rank M. So this is what of constant rank means. And moreover, I want this Jacobian derivative to vary continuously in Z. So again, if you think about orthogonal projections or even radial projections are a nice toy model for this theory. So if you think about what these conditions mean in the context of radial projections, then you'll see that this condition is trivially satisfied for radial projections. So another thing I want to note from point 2, which I'm going to use in point 3, is that, so this is just a consequence of what I've written above. For all z, the map Tz from omega to the Grassmannian manifold consisting of m-dimensional subspaces of Rn, given by Tz of little t, so little t is, as usual, a member of omega. I'm going to define this map by, I take the kernel of the Jacobian derivative of pi t at z. So jz pi t just means the Jacobian derivative of pi t at z. I take the kernel of this map, so it's a rank M map. So the kernel is going to be n minus m dimensional subspace of Rn. And I'm going to take the orthogonal complement of this. So the orthogonal complement of an n minus m dimensional subspace is an m dimensional subspace. So indeed, this map is maps me back into the Grassmannian. So the condition 2 guarantees that this map is well defined almost everywhere. So think rank nullity theorem if you're doing basic linear algebra. So then condition 3 says that for all z in Rn, if I take mu pushed forward by the inverse of this map, so if I take mu pushed forward by tz, so that's this measure lives on the Grassmannian, and I want this to be absolutely continuous with respect to the Grassmannian measure. And this condition is transversality in disguise. So if I'm going to prove a nonlinear projection, the whole reason the Marstrand's projection theorem for orthogonal maps works is that you have this inbuilt transversality in the family of orthogonal projections, or in the family of m-dimensional subspaces of Rn. And transversality is cropped up in all sorts of settings in fractal geometry when you're interested in making sort of almost sure statements. And if I'm going to prove a general nonlinear projection theorem for this family of maps, then I have to have a transversality condition in there somewhere. Otherwise, it's just not going to work. And even though it maybe didn't look clear where that transversality condition is, it's number 3. And again, if you think about this in terms of the radial projections, then you'll see that it's very trivially satisfied. So that's the family, that's the abstract family of maps I'm going to consider. And perhaps I'm going to write the theorem now on the next page, but let me say that this was very much motivated by Perez and Schlag. It's not quite the same family of projections that they consider, but it's highly motivated by their family. So they have a paper on nonlinear projections, and their main motivation was to study the exceptional set in various problems. So in particular, Bernoulli convolutions and sum sets and orthogonal projections, etc. So they have this enormously difficult paper, and this family of projections, which I'm studying, was sort of motivated by what they were doing. So those are the conditions. I don't think it's particularly important that you remember them, but basically I'm taking a family of projections from Rn to Rn, parameterized by t and omega. The second condition tells me that the maps are reasonable. So I want them to be. So I want the projections to be from n-dimensional space to m-dimensional space. So the rank of these maps, so even though these maps are not linear, I want them to be differentiable and their Jacobian be rank m. So this is sort of just allowing me to mimic m-dimensional projections. And the fact that the maps are C1 just tells me that the family varies in a reasonable way. And it's absolutely essential for what I'm going to state next. All of these conditions are essential. So C1 is really needed. And then the third condition is transversality. And the convenient way for me to express transversality is in this, in terms of the absolute continuity with respect to the Grassmannian measure. Okay, so the important thing to remember is just it's an abstract family of projections of Rn. So the theorem says that if I take f in Rn non-empty and bounded, doesn't have to be Borel or compact, but I do want it to be bounded, and that is needed. Then the Assouad dimension of pi t f, so this is this generalized family of projections, is at least what it should be. So the minimum of the Assouad dimension of f and m for mu almost all t and omega. So looks like quite a boring result given how abstract and fancy sounding the conditions were. But basically, I'm showing that you can recover a Marstrand theorem. I mean, this looks like a Marstrand theorem in a much more general setting than just the orthogonal projection. So this theorem immediately implies results for radial projections. It of course implies the result for orthogonal projections, and I can consider all sorts of other families of projections too. So let me just say a few things about this theorem, and then I'm not going to prove it, but I'll tell you some ideas about how to prove it. So I can also study the exceptional set. And actually, the real theorem that I proved was slightly different from the one I've stated, because I can replace the Grassmannian measure with Hausdorff measure of any dimension I want. And so if I have this, the final condition showed that this push forward of mu was absolutely continuous with respect to the Grassmannian measure. If I replace that Grassmannian measure with a Hausdorff measure of some lower dimension, then I can use the theorem to study the exceptional set, the Hausdorff dimension of the exceptional set. So applications include radial projections, cylindrical projections, whatever they are, sum product results, so sum product theory, let me just say. So you might wonder why that's connected to projections, but if I take sort of expressions built from some product phenomena is sort of talking about if I have a set, then either the sum set, which is the set of all sums formed by elements of the set, or the product set, which is the set of all products formed by elements in the set, at least one of these guys must be big. And so one way of capturing the idea that either the sum set or the product set is big is to consider sets like this. So that's the product set of a set F, and then I'm adding the product set to F. And so if I can say that this set is big in some sense, then this says this is a sort of sum product phenomenon. And this can be expressed as a nonlinear projection. If I sort of fix F, or one of these Fs, I allow the point to vary, then I can express elements in this set as a nonlinear projection of the product of F with itself onto R in a nonlinear way. So that's how this sort of thing gets connected. I don't really want to say any more about that. So how is this? Another application is to distance sets, and that's what I really want to talk about. So I'll get to that. So I do want to talk about distance sets. So how does the proof of this work? Well, it makes extensive use of tangents. So the Assouad dimension, this I'll talk about in more detail when I talk about how to prove the distance set stuff. But to prove this, it makes extensive use of tangents, and in particular the characterization of the Assouad dimension as the supremum of the Hausdorff dimension of tangents. And so this is an extremely useful result due to Kan, Mackie, Ojala, Rossi, and also ideas of Furstenberg. Going some form of this theorem goes back to Furstenberg. So also I'm going to need ideas from differential geometry involving fibers of submersions. So this is basically, because these maps are nonlinear, at some point, so orthogonal projections behave extremely well in this setting, because if I take the projection of a tangent, then it's automatically the tangent of a projection. And this is the sort of thing I want to recover in this nonlinear setting. But then the fibers don't behave well at all because it's a nonlinear map. And so, fortunately, there's all sorts of things known about. So the maps that I'm studying are submersions, because they're C1 and they're ranked strictly less than the ambient space. So this is just a term from differential geometry if you haven't heard it before. And then there are all sorts of results from differential geometry on the theory of the fiber. So how well behaved are the fibers if you know your map is a C1 submersion, that sort of thing. So I'm using some ideas from differential geometry. And then the key thing is to linearize, of course. What else could you do with a nonlinear? With a family of nonlinear maps, which are all C1, of course, you're going to linearize. And the linearizing, the reason the linearizing works so well is because it's done at the level of tangents. So it's the maps are nonlinear, but I'm going to study the Assouad dimension by studying the tangents. And so fortunately, when I zoom into a tangent, the map becomes more regular, and so I can linearize it in an effective way. So this is essentially the proof. It's I don't know whether it's difficult or not. I found it difficult, but then again, I eventually did it, so that probably makes it easy. But it's a little technical. I think I would describe it as technical. So I'm not going to prove it, but what I want to do is show you, I'm going to show you how to use this result to prove a result about distance sets. And I really want to get to this proof because this is sort of the whole point. So I'm going to go a little faster maybe. So the key step in proving the previous theorem is actually the following technical lemma. So I just said that when you deal with orthogonal projections, the projections of tangents are tangents of projections. And this lemma says that nonlinear projections of tangents are tangents of projections in some way. So you'll see that flavor come out in this lemma. It looks a little unnatural at first, but if you remember that phrase, projections of tangents or tangents of projections, then hopefully it makes sense. And actually all the work in proving the previous theorem is in proving this lemma. So let me just write it down. So I'm going to, just for convenience, I don't actually need the F to be compact, but let me, for convenience, assume that it is compact. And I'm going to have E be something which I'm going to call a simple tangent to F with focal point Z, and Z is going to be a member of F. So probably people who are familiar with this stuff, they would have expected me to use terminology like weak tangent, but actually, so this is actually what these things are. But instead of setting up weak tangents as I would normally, it's much easier. So we're always having to talk about subsets of weak tangents. So actually, I want the convergence to the tangent with respect to the Hausdorff metric just to be one-sided. So if that doesn't mean anything to you, then don't worry. But just think of these as tangents formed by blowing up the set and taking limits in the Hausdorff metric. But so that I don't have to keep saying subset, I'm only taking convergence from one side. And simple is simply referring to the fact that I am not allowing rotations or anything like this when I blow up the set. So I take the set in Rn and I just magnify it by homotheties, and then I take a limit. And because the set's compact, I must take the limit accumulating at one particular place, and that's the focal point. So okay, I'm not the tangents. What I'm not doing is fixing Z and then zooming in at Z. I'm allowed to zoom in at any point, but then the points which the sequence of points which I'm zooming in at must converge somewhere because it's a compact set, and so the limit of that sequence is what I'm calling the focal point. And it's interesting. I've never had to worry about this before. So I've dealt with weak tangents and Assouad dimension a lot, and this focal point has never mattered, but it matters crucially in this work. And so I thought that was a fun new feature. So F is non-empty and compact, and E is a tangent with focal point Z. So now suppose T is in omega such that capital pi T is C1 of constant rank M in a neighborhood of Z. So in particular, this is true for almost all T by the assumptions of the main theorem. Then the conclusion is the projection of the tangent. So this is now an orthogonal projection onto a subspace V, which I'm yet to specify. So the orthogonal projection of E, which is the tangent, onto V is a tangent to capital pi T of F for V equal the kernel of the derivative of pi T at Z orthogonal, which this, by the way, is capital T Z of T, which is the map I defined in the introduction. So this is where this comes in. And that is m-dimensional subspace of Rn. So this says the projection of a tangent is the tangent of a projection, but all this kernel business is because the maps are nonlinear. So this is the key lemma, and this is what I'm going to use. So this is what's used to prove the main abstract theorem, which I've explained. But actually, the application to the distance sets uses the lemma, not the theorem. So I wanted to show the theorem because that's the sort of Marstrand thing, that this lemma actually contains all the content, and this is the thing that's used to then prove the application to the distance set problem. So, okay, I want to draw a little picture. Okay, let's suppose we're in R2 and we've got rank 1 maps. So these guys are going to move along one-dimensional fibers. So the fibers are going to be one-dimensional manifolds. So maybe if here is Z. So this is the focal point of the tangent E. The fibers of the map pi t are nonlinear, right? They don't have to be lines, and they're mapping onto some. So this is pi t of R2 is this one-dimensional curve, and pi t acts by moving points along these fibers. So in particular, this little guy here, this point here is capital pi t of Z. So we're projecting R2 onto this one-dimensional submanifold along these fibers, which are themselves one-dimensional manifolds. Now, what's happening here? Well, Z was the focal point of this tangent. So F is sort of the usual thing, a fractal sitting here. I'm taking E as a tangent to F at Z. So very, very close. So E is formed by blowing up F in the neighborhood of Z in a homothetic way. Now, how will that reappear when you project it? Well, this guy moves along the fiber lines, and in the end, so, okay, the projection of this little piece of F will be a little piece of the projection down here, but then I'm trying to consider a tangent of this set pi t of F. So even though the manifold is curved, the tangents will live on straight lines because the curve is differentiable because the map is C1. And so there's a straight line here where I can find a tangent to pi t of F living in this straight line, which is simply equal to pi, or the orthogonal projection of the tangent E onto V, for V being this particular subspace. And you can sort of see where this is coming from because it's the fiber, it's the direction of the fiber. It's how do the fibers intersect the small neighborhoods of Z is what's determining this. Okay, so maybe this picture was helpful, maybe it wasn't, but in any case, there it is. Okay, so let me make use of this nice white bit of paper here. So the main result is the following. So I want F to be a subset of R2 with absolutely no additional assumptions. So it doesn't have to be bounded, it doesn't have to be Borel. Then the Assouad dimension of the distance set of F is at least the minimum of the Assouad dimension of F and 1. So if you remember way back at the start, I proposed a stronger version of the distance set problem for Hausdorff dimension. That was exactly this if you set n equal to 2. So there was a 2 divided by n at the start as a coefficient of this thing. But of course here n is 2, so 2 divided by n is 1. So this is the optimal solution to this conjecture where Hausdorff dimension is replaced by Assouad dimension and we're in the plane. And this is sharp. The sharpness is standard. It's been known. It's known before. I don't want to say anything about that. So basically, you can't hope for a better lower bound than this. Okay, so I want to, in the last 6 minutes, this is unfortunate, I don't have all that much time, but let me just whiz through it and then people can ask me questions about it afterwards, if they want. So how I'm going to prove this is essentially just apply the key technical lemma, which I already stated. But there's a couple of tricks which I thought were much cuter than the technical proof of that key lemma. So those are the things I want to emphasize. So I'm going to start by relating the distance set to nonlinear projections. And I'm going to do that as follows. So let me take, I'm just setting this up in R2. So if you want, n can be 2 the whole way through. So this is just S1, the circle. So this is a set of directions, and y is going to be a set of radii. And I'm going to define the radial product of x and y. I'm going to write it like this, simply as x, y, x and x, y and y. And this is a subset, expressed like this is a subset of Rn. Now the key thing, why this is relevant, this seems like unrelated to what I've been saying previously, but the reason why this is relevant is twofold. One, and this is really the main trick, so take nothing else away from the talk, this is probably it. Given any set E in Rn and any point Z in Rn, E is going to be a subset of the radial projection of E in direction Z, translated by Z, radial producted with the distance set pinned at Z of E, and then translated by Z. Like this is the key thing that relates distance sets to nonlinear projections. And hopefully it's clear. I mean, this is a one-line exercise to verify this, but it basically says, if I know the direction, so the direction, so if I fix Z, and then I have another point X, so okay, let me just draw a picture. Here's Z, here's X in E. Then the direction of X from Z is determined by the radial projection. And then the distance between Z and X is given to you by the circular projection, which is the pin distance map. So you just need to do a little bit of algebra and you see that this inclusion holds. So, you know, the projection, this here is the radial projection of X in direction Z, and then I have to translate it back to the origin in order to get a proper set of directions. And then I take the radial product with the distance set, and then I translate it back again and I recover X. So then it's an easy exercise to show that the Hausdorff dimension of X radial product Y is at most the Hausdorff dimension of X plus the upper box dimension of Y. This is just an exercise. And in particular, this tells me that the Assouad dimension of the pinned distance map of E is at least the Hausdorff dimension of E minus the Hausdorff dimension of the radial product of E in direction Z. So this just follows from rearranging this top equation and using the fact that Assouad dimension is bigger than upper box dimension. Okay, so now I'm ready to give the proof, 2 minutes. So I'm going to take E, a tangent to F with focal point Z, and with the Hausdorff dimension of E equal to the Assouad dimension of Z, of F, sorry. And this is the Kahn-Macchi-Ojala-Rossi expression for the Assouad dimension, which I mentioned at the start. So I can always find a tangent with this property. And then I'm going to take E prime, a tangent to E. Sorry, the focal point is for the second line. So E is simply a tangent to F with the correct Hausdorff dimension. E prime is a tangent to E with focal point Z in B. So E prime is a tangent to E, so the focal point is in E. And this has also the correct Hausdorff dimension. So the Hausdorff dimension of E is the Hausdorff dimension of E prime. And then hopefully that's still in focus. And then the final ingredient is curly E is going to be the exceptional set in the linear projection theorem for Assouad dimension, which I mentioned right at the start. So this is the Marstrand type theorem for Assouad dimension. So there's an exceptional set of one-dimensional lines, and I'm going to call that curly E. So this is the exceptional set when the set in question is E prime. Okay, so this is a little bit complicated to follow because there's tangents of tangents, but this is the setup. Now, the proof then works in two cases. I realize I'm basically out of time, but let me just give you the idea of both of these cases. So the first case is, suppose the Hausdorff dimension of the radial projection of E in direction Z is positive. Then, by Orponen's projection theorem, which proved that the E, curly E here has Hausdorff dimension 0, if this set has positive Hausdorff dimension, so by Orponen's theorem, we can find X in E such that the span of Z minus X is not in the exceptional set, because the exceptional set has dimension 0. So if this set has positive dimension, then I can find a good point X such that this direction is not an exceptional direction. Then the Assouad dimension of the distance set of F, which is the thing I want to study, is bounded below, this is not immediate, but this is something which is well known, by the Assouad dimension of the distance set of E, because E is a tangent to F, and moreover I can take the pinned distance set, and the Assouad dimension would only go down because the pinned distance set is a subset and Z belongs to E. Now this is at least the Assouad dimension of the projection onto the span of Z minus X E prime. That's just the key lemma, because I'm establishing that this is a nonlinear projection, and the nonlinear projection of a tangent is a tangent of a nonlinear projection, and the nonlinear projection, the orthogonal projection related to that nonlinear projection is given by this. And then because the direction Z minus X was not exceptional in Orponen's theorem, this is what it should be, namely the minimum of the Assouad dimension of E prime and 1, and that, by assumption, is the Assouad dimension of F, the minimum of the Assouad dimension of F and 1, and so that completes the proof. And case 2 is easier, but it follows using this trick. So remember the trick on the previous page, which I've lost. So the trick on the previous page was where I related distance sets to nonlinear projections. I got this formula for the Assouad dimension of the distance set. So notice, or maybe I can just explain it. It just follows immediately from this, because in case 1, the Hausdorff dimension of this radial projection was positive. So case 2 says the Hausdorff dimension of this radial projection is 0. But then if you plug 0 in here, the Hausdorff dimension of E by assumption was the Assouad dimension of F, and you get the result just directly from applying this inequality. So I'm sorry I'm over time, but I'll stop there. And thanks very much for everyone's attention. Thanks to Ty.
Anyone got any questions? I had a question. Do nonlinear slices make sense in this setup?
Because the maps are C1, then they have C1 or I guess one-dimensional smooth fibers, and so you could look at the intersection of a typical fiber. So yeah, I suppose that makes sense. Yeah.
Wait, Kenneth has put, I think he's going to put a comment in the chat.
So the slicing theorems don't work very well for Assouad dimension. Basically, like slicing is like getting good slicing theorems. You really need a measure theoretically responsible notion of dimension, whereas the Assouad dimension, box dimension, etc., can be carried by countable sets, and so slicing theorems for those dimensions don't really work so well. But you can absolutely ask it for Hausdorff dimension.
Are there any other questions?
I was just going to make a comment, if I may, Natalia.
Yeah.
Yeah, John, you mentioned that you didn't think that John Marstrand was concerned with radial projections, but in fact, there are about 3 sections in his 1954 paper on the matter. In particular, he shows that if you've got a plane set of dimension bigger than 1, then the radial projection from almost all points in the set is a full measure. He makes extensive use of tangents.
As I was saying that, I was imagining that this exact thing would happen, that you would say at the end that actually that's in Marstrand's paper and I should have read it properly. So you're quite right, Ken, thanks.
Cheers.
Are there any other questions or comments? Okay. Well, thanks, John, again.
Thank you, Natalia.